Nope. There we go. Cool. Okay. Let's find my current video. There we go. Sweet. I need to share this somehow. Let's find my current video. Okay. There we go. And then I'll go to Chugan Lu. I think that's how you say it. And I'll invite her and she can come watch. Okay. Where is she? Chugan. Okay, cool. Cool. Yeah. Play some music. Okay. Okay, so I have figured out how to solve this B. Okay, so A is easy. All you do, okay, is you take the variables. Okay. Okay, I'm gonna redo this question in a nice, neat manner so I can add in. Okay, so we've figured out this problem. Okay. Okay, so okay, so I figured out this problem. This is actually quite easy. It's easier than I expected. I was just being dumb. Should have watched the video sooner. Okay, so what we have, well, the primal problem is this. This is our primal problem. This is our primal problem is this. All this is our primal problem. So to solve the primal problem, it's just solving it. You find the optimal by graphing. Okay, you take the bounds. Okay, so what we have is you take these inequalities and you find the bounds. So we know that x1 plus x2 is equal to 3. We treat this as x1, we treat this as x2. Those equations, when you make 1 equal 0, you get 3 and 3. So you get a nice line through, and you get this area, okay? You find the maximum by checking at every point, and there you go. Here's my maximum. It's that simple. That's so easy, mind blown. Question B is where it kind of gets difficult because I didn't really know what a dual problem was. I thought I did, but then like I tried doing it and I'm like, this doesn't make any sense, right? So actually, I watched a video that he suggested, and what we do is we multiply this by 1, multiply this by 2, okay? And we take this. So what we're gonna do is we're gonna have, oh, okay. Can't remember what he did with these though. Oh yeah, okay, well, let me just try this, okay? So let's just write it out real quick. Okay, so we got x1. So what we're gonna do is we're gonna multiply this by this, and we're not actually gonna multiply by x1, a1 by x1. What we're doing is we're taking the coefficient. So the coefficient is gonna be 1, 1, 1, 1, and then whatever, right? So what we'll end up with is a1, and what we're gonna do is we're actually gonna add this to this, right? Oh, actually, before I do that, we do need the inequalities to be the same. So to make it the same, we got to multiply this by -1. So this is actually going to be -1 x1 minus x2 is less than or equal to -2. Okay, that's pretty simple. And then we're going to multiply this by a2. So what we end up getting is a1 plus negative a2. Negative a2. Okay, and this is actually going to equal 1. Okay, so I'm actually going to put that above everything. So we're going to go x1 plus x7, or no, 7x2, and then we're going to have this a1 multiplied by x1 plus x2 is less than or equal 3, and then a2 times negative x1 minus x2 less than or equal to negative 2. Okay, that's pretty easy so far, right? Like, okay. Then what you do is what we were talking about. So what this is going to be a1, so a1 times this coefficient plus a2 times this coefficient, which is negative 1, is equal to this one. So you get a1 minus a2 is equal to, or is less than or equal to, I should less than or equal to 1. Okay, and then same thing, a1 minus a2 is less than or equal to 7. And the minimize part is this time is we reverse it, and what we're minimizing is these. So this would be 3a1 and 3a2, or negative a2, because we got the negative. So our minimal is going to be minimize 3a1 minus 3a2, or no, negative 2a2, 3a1 minus 2a2, and that is our problem. And it's just write the dual problem, and this is our dual problem right here. And we don't want a's, so what they actually do is we just convert it to y's. So what we'll have is y1 minus y2 less than or equal to 1. y1 minus y2 less than or equal to 7, where y1 and y2 are greater than 0, and we're going to minimize y1 3y1 minus 2y2, and that's how you do that. Okay, that seems simple enough, right? That's how you solve that, and like that's our dual problem. This is our dual problem. Cool. We don't have to solve it, doesn't it? Using the ideas from complementary slackness, find the solution to the dual problem. So complementary slackness. So they actually do want us to solve this. Oof. Okay, well, slackness would suggest that. One second. I'm pretty sure this isn't actually max. Pretty sure we gotta flip those inequalities to this. Right? Let me double check. Okay. So for C, we have to do complementary slackness. So let's just rewatch that YouTube video really quickly.
Strains the primal will have. Now, the right hand side values of this is written, then the dual is written. So if this problem such that this is.
It is. Okay, so this is actually this. So that's my fault for not knowing that.
Minimized.
Okay, you flip the inequality when you switch it to the dual problem. So you flip the inequality, and now slackness does make sense, because when you add slackness, so for here, this would be surplus. You'd be, for here, this would be a surplus, right? Alright, here, for the original problem, what you'd do to solve it is you would add a variable. Okay? and that's a surplus. Okay, but for the other way, we have to add a slackness, and so that means we subtract S and we subtract T to minimize it. Okay, to help minimize it. So to solve this, what you do is complementary solve. To do that, you go y1 minus y2 minus S is less than or equal 1. Okay, and then y1 minus y2 minus t is less than or equal to 7. Okay, and then we have the objective function, which is 3i minus 2y2, okay, which is the same as it's always been for now, right? So this is the equations that we'll be using, okay? And this is our z. I should say, call this our z, right? This is our z. So not z equal this. So if we want to solve this, right? Like this is what we want to solve.
And the right hand side values of the dual will be the objective function values of the prime. In a 2 by 2 example such as this, we may end up seeing, for example, we may not.
Okay, so my next thing is that I don't know exactly where to go. Like, when he did the problem, he had it laid side by side. So I'm wondering, is that what we do, or do we just solve it like this, right? Like,
not be able to, we have something other than this. So plus 8x3 strains, coefficient matrix becoming transpose, right hand side becoming objective function, and objective function becoming right hand side. Those things will be there, they will not change. Only these inequalities, the sign of the constraints and the sign of the variables will change depending on how, for any given primal, we can write the dual. Right now we can write the dual if the primal is a maximization problem with all less than or equal to possible types of objective functions, and we would want the dual to have 4 variables. So we do that, and we get this, we get equal to 0, equal to 0. So like this you can interpret, keeping this up.
okay, so we found the one thing to do. Now the next hard thing is figuring out how to solve this, right?
Discussion on the or equal to 0. Very complicated. In fact, the way we have derived the dual, we have already assumed the weak duality here. Because the way we derived the dual, we were only looking at whatever combinations that we saw when we were deriving the dual. They were all feasible solutions to the weak duality, to the dual. And they are all upper bound to the objective function value of the primal at the maximum.
So
there is a now arranging them in terms of x1 and x2. We are grouping them in terms of bound to the objective function value. Now substituting the objective function value of the solution feasible to the dual, we will get. Now w will be greater than or equal to. Now if I have a feasible solution to the dual, then we would have that feasible solution to the dual will be 5y1 plus 12y2. And if we have a feasible solution to the primal x1, x2, then x1 plus x2 is less than or equal to 5. So this solution that is feasible to the dual, which is equal to 5y1 plus 12y2, will be greater than or equal to, because 5 is greater than or equal to x1 plus x2. Now this will be greater than or equal to x1 plus x2 into y1 plus 3x1 plus 2x2 into y2. Now that is shown here. So this feasible solution to the dual w will be greater than or equal to x1 plus x2 into y1 plus 3x1 plus 2x2 into y2. Now when we simplify this, we have x1 plus x2 less than or equal to 5 and 12, substituting we get this. Now rearranging the terms, you would have now w is greater than or equal to x1 into y1 plus 3y2. Look at this expression and look at the next expression. We are now arranging them in terms of x1 and x2. We are grouping them in terms of the terms for x1 and x2. We get y1 plus 3y2 plus y1 plus 2y2. Now since y1, y2 are feasible to the dual, we realize that y1 plus 3y2 is greater than or equal to 6, y1 plus 2y2 is greater than or equal to 5. Substituting,
Oh.
W will be greater than or equal to 6x1 plus 5x2. And since x one next to are feasible to the primal, z is 6x1 plus 5x2, so W is greater than or equal to z. So weak duality theorem is almost a very obvious result the way we have derived the dual. So if the primal and dual have feasible solutions, or for every feasible solution to the primal and every feasible solution to the dual, every feasible solution to the dual will have an objective function value higher than that of every feasible solution to the primal. We can look at it in a different way. If the dual is a minimization problem, every feasible solution to the dual will have an objective function greater than that of the optimum. Primal being a maximization problem, every feasible solution to the primal will be less than or equal to the optimum of the primal. The way we have derived the weak duality theorem, every feasible solution to the dual is an upper bound to the optimum value of to the objective function value at the optimum of the primal, and hence weak duality theorem follows. Weak duality theorem is a very important result. We assume the primal to be maximization, dual minimization. Every feasible solution to the dual will have an objective function value greater than or equal to that.
Okay, so what I've learned is we have to use both the primal and the dual to solve for everything. So we get both these things. We get these two solutions essentially, and now we have to solve for everything. Okay, so we have the primal and we have the dual. So where do we go from here now? Well, this is our dual. Okay, this is our dual. Okay, so now what we have to do is use it for here. Okay. So what we can say is W is greater than everything, blah, blah, blah. What we do is we say that W is equal to x1. Okay, I'm going to lock the screen for a second. Okay, I'm going to bring the screen up, then lock the screen. Okay, so we know that x1 plus 7x2 is our original objective function. Now, we also know that this right here is equal to less than 1 and 7. So what we can actually do is say those coefficients can replace that. So what we get is W is equal to y1 minus y2 times plus 7. Oh no, not 7. y1 minus y2 times x2. Okay.
Of 6 plus 6 equals 12, and have the weak duality theorem I equal to. Now let's go back to the problem. The primal
See,
to the primal, z is 6x1 plus 5x.
She's trying to call me. I don't like it when people try to call me. Not big fan. Don't like calling. Chatting on the phone, not so much. Oh.
y1 plus 3x1 plus 2x2 into y2. Now when we simplify this, we get 1 plus 2 into terms you would have.
She just wants to chat. I do not. Okay, well, we figured out one piece of the
now
problem.
W is greater than or we greater than or equal to. Now if I have a feasible solution to the dual,
now this is kind of difficult because
we would have that feasible solution to the dual will be 5y1 plus 12y2, and if we have feasible to the y1 plus 3x1 plus 2x.
Okay. So what they're saying is if you have a feasible solution here, it'll equal their inequalities essentially. Okay. Substituting into the objective function value of the solution, we get, well, this is what we get right here. Okay. Or we can reverse this. We can actually say W is equal to 3y1 minus 2y2, and then we can have it equal the number, so x1 plus x2 is y1 plus, or no, minus, oh, I guess this would be plus because it's -2, so then we get the negative x1 minus x2 y2, and this is equal to w.
2 into y2. Now when we simplify this, we get, we have x1 plus x2 less than or equal to 5 and 12, substituting we get this. Now rearranging the terms, you would have, now w is greater than or equal to x1 into y1 plus 3y2. Look at this expression and look at the next expression. We are now arranging them in terms of x1 and x2. We are grouping them in terms of the terms for x.
Okay. Okay, and so what they did is they regrouped this. So now we got x1, y1 plus x2, y2 minus y2, x1 minus x2, y2, and then we regroup them for x1. So x1 is going to be y1 minus y2, and then x2 would be plus x2. Oh, minus y1. Ooh, wait. Well, this is, well, essentially going to give us 0. That's what we tried to do earlier, you silly goose. That won't work for us. So she's confusing the dual for the dual problem, which is problematic. So I just went over it.
x1 and x2, we get y1 plus 3y2 can as a, and we are also vectors. The problem maximizing primal and dual relation value is actually the rate of increase of the objective function of the primal for a small increase in one of these resources. If the first resource is increased by a small quantity delta, the objective function will now increase by a quantity 3 delta, where this 3 is the value of the corresponding dual variable. If the second resource is increased or reduced by a small quantity delta, then we can go back and easily show that the objective function will increase or reduce correspondingly by this. X, V, Y, U are all vectors. Because, and somewhere it will be violating the criterion theorem says that if primal and dual have feasible solutions with the same value of the objective function, then those solutions are optimal to the primal and dual respectively.
Okay.
Now the third one is called the main duality theorem.
Main duality theorem. Okay.
If primal and dual have feasible solutions,
okay,
then both have star equal to W star with the same value of the objective.
Okay,
This is a more
so
general statement because it assumes
we're
that
looking
if P
for
and
when
D have
Z
feasible
equals
solutions.
W. Okay.
So the first
That's what
part
we're
of
looking
it
for.
can be looked at more from the fundamental theorem of linear programming. That is the reason we saw the
literally
fundamental
explain
theorem. Now every linear programming
Negative
is
2i2.
either
Yeah.
feasible or has an optimum or unbounded or infeasible. So there are three things. Now it has an optimum, can be unbounded and infeasible.
Okay, so
Now,
if optimum, unbounded,
If
and
we assume that P and D have feasible solutions, it means that neither of them is, or we have to make sure that neither of them is infeasible, because if either the primal or the dual are infeasible, then they will not have feasible solutions. Therefore, this is taken care of. Now, it simply means primal and dual have an optimum or unbounded. Now, if one of them is unbounded, then the weak duality theorem will give us some results. It will make sure that somewhere it will be violating some of the weak duality conditions, because one of them will be having an infinity.
okay, so we're
So
looking
the weak
so that
duality
this
theorem
is
will be violated.
unbounded, not infeasible.
Therefore, we
want
look at the
optimum
situation
solutions.
where both
Okay.
will have feasible solutions, then both should have optimum solution. Otherwise, the weak duality theorem will be violated. In any case, we are not going very deep into these theorems, but and we are also vectors which are slack variables for the dual. Then at the optimum, x into v plus y into u equal to 0, x, v, y, u are all vectors, because and dot product. Therefore,
Negative 1.7. Yes. Yes. That's what I have. Okay. Yes.
or this can be generalized as sigma x xi. And since in the given problem x, y, u, v are all greater than or equal to 0, you variables in the primal, dual optimum, subject z y1 plus 3y2 minus v1 equal to 6, v1 makes u1 equal to 0, y1.
Okay, so okay. So essentially what it's saying is we do both the dual theories for both. No. Having a negative does not mean that. Above 0. So what she thinks is because there's a negative, your coefficient is negative, not y. So is equal to -1. Silly. Okay, anyways, so we gotta take this. Okay. So we'll make this C. So first we'll write out the first problem. We've got x1 plus 7x2. And what we're going to do is we're going to make that equal z. Who's graph and solve? I knew. Okay, so plus 2 less than or equal to negative 2. Okay. This. Okay, I'll bring this up. Huh? Oh, I know. Well, I said to come like watch and chat, but she didn't want to do that, so I was like, okay. Well, it's easier for her to ask me questions on here. Yeah. I said what I was gonna do. She didn't want to listen. Not my fault. Okay. So we have this, and then we want the dual problem, and our dual problem was yes. I don't. Okay. And then. Okay. Then, alright. We also have to make sure that this is greater than 0. And this is maximize. Then our dual problem, which is minimize, is going to be 3y 1 minus 2y 2, and this is going to equal w. And this is minimize. And then if I remember this correctly, which I do, it's y1 minus y2 is greater than or equal to 1, and then we got negative, oh no, then we got y1 minus y2 is less than or equal to 7. Okay. I don't know. Okay, now this is where we want to do complementary slacks. So how am I confusing? You keep asking me questions. I don't know. I haven't done this part yet. No, you're just not letting me do it. Okay, anyway, so complementary slacks. So what we do here is what we're going to do is we're going to add slack variables plus x2 plus s minus 3 minus x1 minus x2 minus plus t. I know. I'm doing. Okay, in which case this is less than negative 2. Okay, and then this becomes x1, x2, s and t is greater than 0. And then for this one, we add complementary, what's it called? Oh, I guess this is s1, s2. This is where we add, not slack variables, surplus variables. So, complementary slack variables. So, we're going to say t1 greater than 1. It's y1, y2, y1 minus y2 minus t2 less than or equal to 7, y1, y2, negative t1, negative t2, and then these are all greater than 0. So.
1, y2, v1, v2
Okay,
greater than
so we figured out that much part.
First, let us look at the solutions and then verify the complementary slackness, and then let us go back and do something more with the complementary slackness. So, primal has a solution which is x1 equal to 2, x2 equal to 3, z equal to 27.
Okay, so now
x1 equal to 2, x2 equal to 3 makes u1
so
equal
our
to
solutions
0, u2 equal to 0, z equal to 27. Now, let us assume we know the optimal solution to the dual. So, optimal solution to the dual is something is shown here on the PowerPoint slide. x2 v2 is 0, y1
okay. Complementary slackness.
u1 is 0, y2 plus up to 6y3. This problem is the problem of slackness from that. So, complementary slackness is now satisfied at the optimum. Now, let us do something else. Let us go back and see that same thing is shown here on the PowerPoint slide. The fact that we written the primal and the dual, and we can verify the complementary slackness from that in one of the early lectures. Now, for this problem, the optimal solution to the primal is x1 star equal to 6, x2 star equal to 6, u3 star equal to 6, if you equal to 42. x1, y1 equal to 1, y2 equal to 1, and the rest of them are 0. So, you will have y3 equal to 0, we have v1 equal to 0, v2 equal to 0. The primal had 3 constraints, so we have 3 basic variables, u1 equal to 0. If you apply the complementary slackness to this, you realize the x1.
Okay.
Now, let us go back to that solution. x1 equal to 6, x2 equal to 6, u3 equal to 6, u1 equal to 0, u2 equal to 0. This is the optimal solution to the primal. Optimal solution to the dual is y1 equal to 1,
I think what you
y1 equal to 1, y2 equal to 1, and the rest of them are 0. So, you will have y3 equal to 0, we have v1 equal to 0, v2 there is a equal to 0. You can go back to this example, and then using the complementary slackness condition, the optimal solution to the dual will have w equal to 27. Let us assume we do not know which are the basic variables at the optimum and what values they take. Now, we can find that out using the complementary slackness. Now, this is the optimal solution to the primal. So, x1 is basic, so v1 is non-basic.
So, we know the optimal solution right here. So, our optimal
and equal to 0. x2 is basic, v2 is non-basic and equal to 0. u1 equal to 0, u2 equal to 0 implies y1 and y2 are basic. So, all we need to do is go back and substitute here, substitute v1 equal to 0, v2 equal to 0. If we solve y1 plus 3 y2 equal to 6, y1 plus 2 y2 equal to 5, the values that y1 and y2 will take are optimal, and they turn out to be 3, 1 with the value 27. Similarly, you can go back to this example, and then u2 equal to 5, the values that y1 and y2 will take are optimal, and they turn out to be 3, 1. The optimal solution to the dual will have w equal to 27. Let us assume we do not know which are the basic variables at the optimum and what values they take. Now, we can find that out using the complementary slackness. Now, this is the optimal solution to the primal. So, x1 is basic, so v1 is non-basic
and
equal to 0.
So what we say
x2 is
this
basic,
is 21
v2
equal
is
to
non-basic and equal to 0.
3y1.
u1 equal to 0, u2 equal to 0 implies y1 and
what we
y2
have is
are
1.
basic. So all we need to do is go back and substitute here. Substitute v1 equal to 0, v2 equal to 0. If we solve y1 plus 3y2 equal to 6, y1 plus 2y2 equal to 5, the values that y1 and y2 will take are optimal, and they turn out to be 3, 1 implies y1 and y2 are basic. So all we need, the optimal solution to the dual will have w equal to 27. Let us assume we don't know which are the basic variables at the optimum and what values they take. Now we can find that out using the complementary slackness. Now this is the optimal solution to the primal. So x1 is basic, so v1 is non-basic and equal to 0. x2 is basic, v2 is non-basic and equal to 0.
Okay, so
u1 equal to 0,
x1
u2 equal to
and
0 implies
x2
y1
is
and
basic.
y2 are
So
basic. So all we need to do is go back and substitute here.
y2 is non-basic.
Substitute v1 equal to 0, v2 equal to 0. If we solve y1 plus 3y2 equal to 6, y1 plus 2y2 equal to 5, the values that y1 and y2 will take are optimal,
Okay,
and they turn out to be 3, 1 with the value.
Okay. So let's go over this. So we know we have a solutions. Okay, the solutions for this is we know that to maximize this, we know that it's 3 times 7 is equal to 21. Okay, so if I put 3 in here and this 0, I'll get 21. And this will work because if I put 3 here, I'll get negative 3, negative 0, which is negative 3, which is less than negative 2. Perfect. Like it satisfies that, and it gives me 21. And we know that from here. Okay, like we pick this point, this gives 0, 3, 21. Okay, so we know a solution for this. So if we know a solution, what we have to do, okay, is the optimal solution, as we're going to say optimal solution is when x1 is equal to 0, x2 is equal to 3, okay, go away, okay, we know s1 is equal to 0 and s2 is equal to 0, okay, now vice versa, our non-basic variables are x1, s1, s2, and our basic variables are x2. Vice versa, our non-basic are, okay, so whatever is non-basic here becomes basic, and whatever is basic here becomes non-basic. So our non-basic is x2, and our basic becomes x1, or no, I should say y2, complementary, y1, t1, and t2. So now that we know that, we can solve for this. Oh, also when z is equal to 21, so w has to equal 21 on this side, okay, because they have to if it's optimal for both, it's optimal, right? They're both optimal. So now that we know this, y2 is our basic variable, so what we can actually do is say it's equal to 0, okay, y2 is equal to 0. So what we have here is y2, which is 0 minus y2 minus t1 is less than 1. We're actually going to say that's 0, so let's just do that right now. Minus 0 minus t1 less than or equal to 1. And then y1 minus 0 again, t2 less than or equal to 7. Okay? These are our complementary surplus variables, or complementary slack variables, which are surplus variables. Okay.
27. Similarly, you can go back to this example and then using the complementary slackness conditions and the optimal solution to the primal, you can
now with this is we just solve. We actually solve this, and when I say this is equal to 21, we actually know that this is equal to 3y1 minus 2y2. Okay. Cool. Now what we do is we do the simplex method. So the simplex method is this. We're gonna move this down. Okay, and we're gonna solve for this. So first we're gonna take our constraints, which is we get y1. I'm gonna bring this down like right here. Okay. y1, y2, t1, t2, w. Okay. These are all our variables here. Okay, we're gonna separate them out. Okay, our objective function goes on the bottom. So our objective function was 3 minus 2, 0, 0, and our w was equal to 1. Oh, right. It's going to be negative 1? No. We're flipping these around. This is 3. Negative 3, this is plus 2. W is 1, and then this is 21. Yes. Okay. Then for this, we have 1, 1, 0, 0, and negative 1. So we get negative 1 here, 0, 0, negative 1 here. We get 0, 0, and we get 1 and 7. Okay, and this is what we gotta solve. And it's really just matrixy math. Okay, so we're gonna go and we got to figure out our pivot points and our pivot columns. So pivot point is going to be our negative number, this one right here. So we have our P here, and then it's going to be, out of these two, we need a pivot row. So we have our pivot column, we need a pivot row. It's going to be, we're going to divide this by this number and get whatever the lowest is our pivot column. So 1 divided by 1 is 1, and 7 divided by 1 is 7, and so it's obviously this one. Okay. Well, that seems simple enough. Okay, so in order to get rid of, we got to start getting rid of stuff, and I'm going to get rid of, so we start off with this one. We're trying to get rid of this row and then this column. So in order to do that, we're going to bring this down. And, okay. Okay, so I'm actually going to keep that number out. We're going to keep this number here because this one will not change, but everything else will. So to get rid of this one, I just have to multiply this entire row by -1 and add it to this. So multiply -1 by 1 plus 1 is 0. 0 is still 0. -1 times -1 plus 0 is 1. 0, so this is -1, 0, and then -1 plus 7 is 6. Okay, and then we want to get rid of this row, the -3 plus 2 to 21. So to get rid of this -3, I have to multiply this entire top row by 3 and just add. Okay, so that's going to get rid of that right away. Okay, the 2 is going to remain because 0 times 3 plus 2 is still 2. We still have this number to deal with, right? Okay, do that. So you'll see that there's a 0 here, so we multiply by -3, which will give us 3, so this becomes 3. This comes down to 0, 0, and then 1 times 1 times 3. Oh, wait. It's not negative. I'm just multiplying by 3. Okay, so 3 times this, I'll get a -3 here. Okay, that's important. That's actually really important because otherwise I've finished and I've been done in my head and I'd have messed up. But anyways, I'm just multiplying by 3 because this is a -3. So I just have to multiply by 3 and add it to get rid of it. Okay. So then 3 times this plus 21 is going to be 24. Okay. And to show my work, obviously, what I gotta do is I just say row 1 times -1 plus row 2, and row 1 times 3 plus row 3. Okay, so that's what I did. That's how I'm showing it. Right, easy peasy. And then we're just gonna bring this up here. Okay, so we actually have to do this again. We we have to make a nice, let's see, T1, T2, W, then this. Okay, so we're going to be doing this again. This time though, we have a new pivot column. So again, -3 is right here. And then again, what we do is, so we have to find the least negative without negative. So this has to be our pivot. We can't use the negative for a pivot, unfortunately. So that means that these are 2 pivots now. So what we're going to do is we got to get rid of this column next. So in order to do that, we just add this upward. Okay, so that's it. So first we're going to keep the same row. So 0, 0, -1, no, +1, -1, 0, 6. Okay, and then 0, 0. And, oh no, we keep this 2. Now none of this is going to change. Okay, so we're going to do the top row first. So that's going to be 0. We're going to get -1 here, and we're going to get 7 there. So we're going to get 0, -1 here. It stays 0, I'm pretty sure. Yeah, and we're going to get 7. And then everything else is the same, so 1, 0, 0. Okay, and then we still have to get rid of the -3. Obviously, I'm just going to multiply by 3, so that's going to be 0. And this is going to become -3. This is going to stay 1. -3 times, or no, 3 times 6 is 18 plus 24. So 12 plus 24 would be 38, 44, I think. Let me double check. I can't do math. 24 plus 18. 42. Bad at math. Okay. So, now we've done the simplex method. Again, we gotta do this, but check this out. We do P, and we can't use this here. Right? It feels off there, though. No, that's right. Okay, so for this one, now we've seen what it is. We have what is it? I think Y1 and Y2. Okay, so this was our Y1, and then when we did this again, this became our T1. So Y1, T1. Okay, and yeah, so what we have is Y1 is equal to 7, T1 equal to 6, and our W equals 42. Okay? And that's supposed to be our solution. So if we do that right, that means that T2 is equal to 0 and R2 is equal to 0. Okay, so to test that, what we do is we just go back and we plug it in, which is easy. If I make that 0, Y2 becomes 1. Oh, so Y1 is 7, so 3 times Y is 21, and this is 0. That's it. Okay, so let's see. Let me ask her. I'm pretty sure she said that was her answer. So she's like, tell me if I did it right. I'm like, I think you did it right. I'm pretty sure you did it right. Let's ask her. Yeah, I got 0, 7, 0. Yeah, I got 7, 0, 2. Okay, so we got the optimal solution. Is Bam! Cool. Now, that's a lot of work. Okay, so that was that one. Now we got this one. Now this is where we have we only have one inequality, right? Solve the dual problem. Interesting. Okay, well, let's write out the dual problem. Like, okay, so how this is going to turn out, this is going to be cool. So what we get is 2x1 plus 3x2 plus 4x3 plus x4. And then we get x1 plus 2x2 plus 5x3 plus x4 less than or equal to 12. Okay, so that's what we get. That doesn't seem very like intuitive, but like, huh? What? No, I got y1 is equal to 7. I said y1, not fucking your y1 is equal to 7, and y2 is equal to 0, and t1 plus t2 what is it? T1 is equal to 0? No, T1 was equal to something else. T1 was like 7 or 8, whatever. W is equal to 1. Yeah. So that should make sense. If you were watching me, you would know what I was doing, like I suggested. But no, nobody wants to listen to me. Okay, if you watch me, I could teach you. Or confirm. But you don't want to watch me, or it's not working, and I can't help with that. But okay, we're going to write out the dual problem. So, if I'm going to write out the dual problem, what I'm going to do is, it's actually quite easy. It's going to be y1 is greater than or equal to 2. I just started it. Okay, I think I got this now. Okay, frick, I hate technology sometimes, just hate it. It is sometimes the bane of my existence, honestly. Okay, let's see, can we focus this? There we go. Can we make this more straight for you? Here we go. Okay, so the dual problem is we're going to turn this into a dual problem. So, dual. Okay, we want dual. Okay, so what this is going to become is y1 is greater than equal to 2. y2 watch working on it on my stream. Okay. Then we get y2. We get 2. This is our 2y1 right here. And it's going to be greater than 3. It's going to be 5y3. It's greater than or equal to 4. I don't even know how the... Oh, well, that just makes sense. There's no way you can equal to 4. No, there isn't. Oh yeah, there is 1/4 or 1/5. No. I can't think of it. Anyways, 4/5. 4/5? Yes. Okay. Then we get, well, y4 is greater than 1. Okay. Oh, and y1, y2, y3, y4 is all greater than 0. Okay, and then our objective function is going to be this 12. That's it. Right? 12y1. Okay. 1 second. Yeah. 12y1 is equal to W. Equal to W. Okay, that's our objective function, and we want to minimize. Okay, so what it says is write the dual problem and then solve the dual problem. Okay. Oh, this is all y1. That's all y1. Watch. On PC. Okay, so we just have to follow these constraints, and that's actually quite easy. Like, we could, there's a few ways, but like essentially we get this graph, right? And we're saying it's a line. It's essentially a line. These are just lines, essentially, and we just have to find the area. So this is easy, I think. So let's try the graphic method, because the graphing method might be the best way to go here. So we're gonna go like that, nice big line. Yeah. Okay. Now, let's go through these. So we got y1 is greater than 2. Okay, so 2. Okay. y1 is greater than 3. It's everything above this. 5. Okay. Oh. This is just y1 greater than 0. No. Let's no. So what we're looking for is a feasible region that satisfies all of this, all these things. Okay. That's what I'm saying. Okay. We're looking for a feasible region that satisfies all these. Now this, what if we make this equal to 4? If you see that this is equal to 4. Okay, like, so this is greater than 1. That's what we know. So like if we went from there, it'd be like this, all the way down to 0. Okay? Then we have 1, which is right here, is 1. So the feasible region would be anything above the highest one, essentially. That's what we really have to be considerate of, is just that, and it sounds and looks like it's unbounded. Which might be a problem. Definitely. That's what I'm thinking. Right? Because we get all these things, like, we write the dual problem, here's our dual problem. Okay? It's not very difficult because we do literally the same thing that we did for this one. Okay? for this one, it's just what we have is y1 is greater than 2. We have all these things that are just greater than. So like, the only feasible region would be the highest one and be above, which is, to me seems like an issue. The reason it seems like an issue is because, oh wait, we're trying to minimize. That actually is beneficial, because if it was like, even though it's unbounded upwards, the minimum is going to be everything of these. So let's see, we get 1 at 2, right? We get 1 at 1, so it can't be these two. We go up one more, right? So for this one, it'd be 4 over 5, right? Because if I put 4 over 5 here, that would equal 4. So when y1 is equal to 4 over 5, where's 4 over 5? That's 0.8, that's below 1. And then for this one, it's 3 over 2. Yeah. So, which should be less than 1, I'm pretty sure. Yep, 1.5. So the most feasible region is at 2. Okay. So what we have here is a bunch of ones that are like this. Okay. But the most minimum that satisfies all this is when y1 is equal to 2. So we just put that in. 12 to 2 is equal to 24. W is equal to 24. This is our minimum. Okay, that's our minimum. Now that we have this, we need our maximum. How do we do that? We use B to determine this solution. So we want this to equal 24. So kind of confused. So when we did that, x1, so y1 was non-basic. So our x1 is going to be our basic. No, y1 was basic, so y1 is going to be our non-basic. So x1 is going to be non-basic. It is going to be non-basic. And then x2, x3, x4, x4 is going to be our basic ones. Okay, so if that's our basic, okay, so x2, x3, x4s are going to be our basic, then what do we do with them? We add a slack variable, which is going to be s. Oh, so in this, I should mention that x3 and x4 are unrestricted. So when you do that, actually in unrestricted, what you're supposed to do is give it 2 variables. I'm pretty sure. Like A1 minus A2 and A3 minus A4. And solve. Makes things more. Okay. So, you know x1s are non-basic. We also know x3 and x4 are unrestricted, I guess. But we also know that this is going to equal 24. So, I feel like I did something wrong. now we just have to solve from here. Okay, this is what we have to solve now. Okay, and what can we do to do that? I don't know. So now we come back, because now that we've solved the dual problem, we said it's pretty simple once you break it down. Now we have to use B to determine the optimal solution to the primal problem. Okay, that is problematic. Well, we know y1 is equal to what? No, that wouldn't work. Okay, so if we made this equal 12, what we could do, and this is just me thinking outside the box here, is we could say that x1 plus 2, x2 plus 5x3 plus x4 is times y1, which is going to equal 24, when y1 is equal to 2. Okay. Now that does not a lot for me. Like, it does some things, because now I can multiply by 2 and it equals 24. But now we have all these variables that don't equal anything. Well, we know this, it has to be non-basic. So that reduces this to a 0, and then we are left with x2, x3, x4. Right? x2, x3, x4 as our non-basic variables, and that's a lot of frickin' non-basic variables. How do I solve this? I don't know, guys. I just don't know. What did we do? What did we do to get the dual problem? That's the real question. How did we get just this dual problem? Well, we took these, multiplied it by y, and then that's how we got this, right? Like, I suppose I could take this. It's going to be 0, 0, so it would be these, right? I could try that. Okay, you know what? That's something I'm going to try. Okay, so this was A and B. Okay. I just want to say. Okay. So, I'm actually going to make this a little bit darker. I don't like the light blue right now, especially for streaming, you know? I'm going to make this a little bit thicker so that my writing is nice and legible to everybody. So what we're going to say is the most minimum we should write it like this, actually. One second. Less than equal to that, because that's actually what that is. Truly, you can actually go higher, right, than W. But the most minimum 12y1 equaling W is where y1 is in the feasible zone at its lowest point, which is 2, which is y1 equaling 2. Thus, w is equal to 12 times 2, which is 24. Okay. Easy solution. Okay, now we have to solve for B, finding the optimal solution to the primal problem. The primal problem being this right here. This is our primal problem. So what I'm going to do is I'm going to zoom the frick in. We're going to go over here. Have some nice room over here. Okay, here's our C. Okay, C, and we want to solve this. So to solve this, what's the most beneficial way to do that? Well, we just have to find the dual problem. So our basic variable for the primal problem will be x2, x3, x4, and s. I didn't use any slack variables in the last one. I didn't need any slack variables mostly. Like I guess I could have used them, but like it really doesn't make any sense. It's all y1, right? S. T would have been my slack variable or my surplus variable over there, but like I don't need it here. I might need it, so I'll just add it. See what happens. Primal problem will be x2, x3, x4, s. Okay. Our non-basic is x1, because if it's x1, y1 sort of thing, right? Like complementary, that is our non-basic. So x1 is 0. So now that we have that, what we can do is we're going to take the optimal w equaling z. So we make z equal 24, I believe. Make z equal 24. Dakota Meister. What's up, Dakota Meister? How goes it? I'm just learning how to do some operations research duality problems. Kind of difficult for me. So going through it through my head right now. Okay. So now we say z is equal to 24. Okay. We have this. So we can actually get rid of this and this. So we're going to say 3x2, 4x3, x4. Go into 3x2, 4x3, x4. 3x2, 4x3, x4. So what we have is 3x2, 4x3, and we're going to say 0 here, plus x4 is equal to 21. And then this is going to be 12, and that is x1, 2x2, also 0, 2x2, 5x3 plus x4, 5x3 plus x4. Okay, and that's the duality problem that we want to solve. So, oh, and we're adding a t actually, plus t, plus s. Okay, and then we do the simplex method. So we go x1, x2, x3, x4, s, and then yeah, and this is w equaling 21, so we'll say z. So, okay, but we're saying this is z, and we're keeping that 1, so these all become negative, so this becomes 0, -3, -4, -1. This is going to be our 1, and this is going to be 21. Because z is actually equal to 21. Yeah! Actually, what we could do is make it 21. Yes. something's wrong here. I feel like I did something wrong with the last one too. If we make z equal 21, then it should just be 21, right? So you don't actually use z, you just say z0. And have that as 21. Okay, well I did something wrong with the last one, but I'm not going to change it, so it's okay. Okay, and then this, ooh, it's actually just one line. So let's see, we get 2, 5, 2, 5, and x4 is 1. Okay. And then we just want to solve for this, right? Like, so first we gotta take the most negative, which is gonna be here and here. So pivot row, pivot column, there it is. That's actually easy. And we want to make that a 1, so okay. Okay, so we'll divide by 5. So we get 2 over 5, 1, 1 over 5, 1 over 5, 0, and then we get negative 3, negative 4, negative 1, 0, and then we just have to solve. So x1, x2, x3, x4, s. Okay, we have 12. And we keep this one, so we get 2 over 5, 1, 1 over 5, 1 over 5, I believe. Yep. And then we gotta figure out how to multiply this to get rid of this. So I just multiply by 4 and add it. So that's what I'll be doing. To go from here to here, we just say row 1 times 1 over 5. That's it. And then we're going to say row 1 times 4 plus row 2. So that's going to be 0 right out the gates, times 4 over 5, 3 over 5. So 4 over 5, 4 times 2 is 8 over 5. We have to multiply 8 over 5 to do fractions. We have to multiply 3 by 5, so that's 15 over 5. 15 over 5 plus 14. 15 over 5, negative 15 over 5 plus 8 over 5 is going to give you negative 7 over 5. Ew. Then same thing here, this is going to be a negative 1. We just multiply it by 5. Yep. So you get negative 5 over 5. 4 over 5, you get negative 1 over 5. And then this is just 4 over 5. This is 12 times 4, which is 48 plus 21. 48 plus 21 is what, 69? Let's just double check that. 4 times 12 plus 21. 69. 69. Sorry. Anyway, so but we still have an issue. We still have negatives. This one is not fully negative. This one would be nice negative. So we go here, we get 2 over 5. And how do we get rid of that 2 over 5? Well, we multiply it by 5 over 2. So we get 1. 5 over 2. So we get 5 over 2. We get 5 over 2, 1 half. 5 over 2, 1 half, times 5, 12, times 5, 5 by 2, 30, sweet. Zero, 1, 5, 4, 5, 69. Now, we have to get rid of, well, everything else. So this is going to be 0. This is times 7 over 5. So 15 times 2. 5 over 2. 5. Damn it. 5 over 2 times 7 over 5. So what's going to happen is I'm going to get 7 over 2. Yeah. 7 over 2. And then 5 over 2. Or no. 5 over 7 over 2. Wait, 5 over 2. Yes. But the 5 don't count. This is going to be 7 over 10. Ooh, wait. 7 over 10. This is so hard. You're an evil calculator machine. Okay. Okay, we'll do this right. Because I'm just going to confuse myself if I don't. That's not nice. Okay, we're keeping this. It's been 0, 1, 5 over 2. 1 over 2, 1 over 2. Okay, this is going to be 0 because I'm multiplying by 7 over 5. 7 over 5. It's going to be 7 over 2 here. Okay, that's easy. Okay. 7 over 5. 7 over 5 times 1 over 2 is 7 over 10. I'm going to multiply this by 2, so... I need to multiply this by in half, that's it, don't I? Yes. I need to actually just see this, 1 second. So 1/2 plus negative 1 over 5. I want to make, we're doing 7 over 10, right? So if I want to do this, I have to multiply this by 2, top and bottom. So what we get is negative 2 over 10. This is going to be 5 over 10, 1/2. Okay. So we get 1/2. And then this is 7 over 5, which is 7 over 10, plus 4 or 5, so 8 tenths. It's going to be 15 over 10, which is going to be 3 halves. Divided by 5, so we get 3 halves. Then we get 7 times 30 over 2, 7 over 2. Oh, it's 5, right? 7 times 30 divided by 5. 42. 42 plus 69. It's going to be easy. 111. Okay. So our new pivot was x2. So that's x2 is equaling 30. And everything else becomes 0. So x4, 0. S is 0. And x1 was already 0. So let's test that out. There's only one way to test it out, and that is to put it in. x2 times 30. It's not seem right. That's because it's not right. There's no way x2 times 3 is 30! Fuck! I would have had to do something wrong, right? X2 would have to be 8 in order for it to be 30, and everything else is 0. One second, let me just double check. all the seems wrong. Okay, we're gonna take this. Delete. I want to see the garbage answer anymore. Okay. So essentially what I did the last time, and what did it for whatever reason, was I made this equal to z plus 21. Or 24. Which would be problematic because that's not what it is, right? It's just 24. Right? That's the answer we're looking for. So that makes a lot of sense. So what did I do wrong here? Well, it could be. And I guess what does kind of make sense is if we say this is z, and we solve this. So that we have negative 3x2, negative 4x3, negative 9x4 is equal to 0. When we make the simplex table, as we do, x1, x2, x3, x4, s, and z, and we'll go like this. We're going to say that this is 0, right? Because we no longer have a variable. All that equals 24. Z is 24. But we never said that Z was. Actually, 0, 2, 5, 1, 1, 0. Okay, we don't actually need Z. That's what I'm feeling right now, but I just did it and like it didn't work, right? Like we didn't get this to work. Oh, and these are all negative. Negative 3. Oh, in order for these to be negative though, and if these, this would have to be negative 24. Right? Because in order for this to be negative at all, we have 24. If I bring this to this side, well, we still have 24. Well, I need negative, so this has to be negative. Ah, maybe that's what I did wrong. So again, we're going to go like this. These are pivot columns. And now we're going to go through this again, and I should end up with a more respectable answer. Okay, so we have 12. Actually, no, we have our pivot, so we have to divide by 5. So we get 1 over 5, 1 over 5, 12 over 5, and 2 over 5. And then we have to add it to this bottom one. So 0. So I just multiplied this by 4. And now I multiply this by 4. It's 8 over 5, 8 over 5, 15 over 5, negative 7 over 5. Okay. This is 4 over 5. This is going to be negative 5 over 5. This will be negative 1 over 5. And then this is going to be 4 over 5. And then we get 12 over 5. So I multiply it by 4. 12 times 4, which is 48 over 5, plus minus 24. So we have to multiply 24 by 5. 24 times 5. So 120 minus 48. That's negative 72 over 5. Okay. So what we did here is row reduce. I'm just going to say row reduce echelon. We're going to come up here now. I have no idea what we're listening to. Okay. Yep, 12 over 5. Oh, we gotta select our new pivot actually. So let's select our new pivot. Our new pivot is going to be, this is probably our lowest one right here. So we get P, and so P obviously, so 2 over 5. We multiply by 5 over 2. So what we're going to say is row 1 times 5 over 2. It's going to give us 1. 5 over 2, 1 half. Oh wait, that's actually going to be 5 over 2. 1 half and 1 half. Okay, and then 5 over 2. So this is just going to be 6. And the bottom is negative 72 over 5. Okay, but we're not actually going to keep that because we got to reduce downward again. So how do I get rid of 7 over 5? I multiply by 7 over 5 and I get 0. So that's going to go away. 7 over 5. 7 over 5. What did I do? I multiplied by these 2's. They should be 2's, right? There are 2's here. 7 over 5. Okay, multiply this by 7 over 5, which would be 7 over 2. So 7 over 5, 7 over 10. 7 over 10 plus negative 2 over 10. Wait, because I have to multiply by 2 on top and bottom because they're 5, so that's 5 over 10, 1 half. And then 5 over 10, 7 over 10 plus 8 over 10. 15 over 10, 2/3, 3 halves. Okay, 7 times 6 over 5. 42 over 5. We have 42 over 5 plus 72 over 5. It's 30 over 5. 30 divided by 5 is 6. This is negative 6. This is our answer. Okay. 6. No. Oh, we finally got it. X2 is equal to 6. X3 is equal to 0. X4 is equal to 0. xs is equal to 0. They're all freaking non-basic. Now we know. This is our solution. Z is equal to 24. We have found it. Yes! And this is our solution. And it works because if we go back here, if we put 6 here, 6 times 3, that is wrong. It should be 8. What is the 80? What did I do wrong? 12 times 7. 12 times 7. How did I get the 6? How I got that 6 was multiplied by 5 over 2. 12 times 5. So the 5's were cancelled out, and over 2 it gave me 6. There we go. Okay. And then I multiplied it by 7 5s. Okay. Gave me 42. 42 minus 72 is 30 divided by 5. Which is is that x3 is equal to 12 over 5 times 4. There's something wrong here. I feel like it's right here. No. There's too many steps in one place. Okay. So, how did I get here? How do I go from here to here? This is going to be 12 times 2. Okay, I said I divided everything by 5. That's how I get 12 over 5. Then, we get rid of this number. You do this by multiplying by 4. So 4 0. So 12 times 4 over 5 is 48. So we get 48 over 5. And we add it to 24 negative times 5 over 5. So 24 times 5 minus 48 is 72 over 5. This is an optimal solution. It doesn't give us 24, you whore. This becomes negative 6. Look at this. Yeah, let me just get my life here. X2 becomes 6. If X2 is 4, I don't know. I feel like I was closer earlier, but now I just don't get it. Okay, so we don't have a lot of inequalities. Right? Like, something here isn't adding up. That's what I'm seeing. Just don't know what it is. No try satisfied. Now x3 and x4 are unrestricted, so I guess I could just say okay, let's just check out something. Okay, let's go to 330, no, Math 360. Let's click up. I wanted to go to my university. That's what I want to go. Check out my emails. Yeah. And not have it work because lights up. Yeah. So let's go. We're going to check out the emails. So we're going to go in. We're going to figure this out. Okay. I'm looking for when we don't have a lot of constraints. Oh, so instead of just saying, hey, like using simplex because that, we can actually just solve. We're like, well, okay, we're like, is equal to z24. So how can we make this equal 24? Well, there's a few ways. We could say x3 is equal to 6. There you go. Equals 0, x2 is equal to 0, and x1 is equal to 0. There you go. And that's our solution. We don't have to do anything about that. Cool. Next. Hey, it's the last question, and artificial variables. Without artificial variables, what do you mean? Okay, well, first things first, we're going to take this, multiply it by -1. Where this is, she's going to give us 5x1 minus 2x2 4. Okay. Now, dun, 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 dun. This is the best song in that whole game. Okay. So we're gonna do that. Can we make this from all this? I feel like we can. Okay, so the primal problem. Okay, so we're gonna go primal. Let's go with a darker color, like purple. Purple's a good color for this. Primal. Okay. Minimize 9x1 plus 3x2 for 4x1 greater than 12 2x1 plus 4x2 is greater than 22. 5x1 plus 2x2, negative 5x1, negative 2x2 is greater than 30, negative 5x1, negative 2x2 is greater than okay. Okay, that's our final problem. Okay, and then we're gonna do a minimum for our dual. Okay, our dual is maximized. Okay, and we're maximizing that. So if we're gonna make this y1, y2, right up this line. Okay. Okay, so maximize 12 y1 plus 22 y2 plus minus 34 y3. Okay. And then 4 to negative 5. So what we have is 4y1 plus 2y2 minus 5y3 is greater than or equal to 9. Equal to 3. Hey. Okay, so we have this dual problem, and it wants us to maximize this and minimize this, right? Like, solve the following LP problem, use a dual simplex method without artificial variables. Okay, so I don't quite know what the dual simplex method is. introduce soft, we can introduce artificial. But soft variables were artificial. Dual simplex method right here. So you can add a select variable. Before doing the primal problem, and then add it here. So we could add it here and put it here. That changes things, just uses the whole thing. Now, two simplex method. Kind of difficult because let's look it up. Dual S. So dual simplex. Okay.
Grammarly does more than catch errors. With Grammarly, you can find really good, no, perfect words that make your writing sharp, or explicit, or excellent, or distinct.
हेलो स्टूडेंट, इस वीडियो में हम लोग स्टार्ट करने जा रहे हैं ड्यूअल सिंप्लेक्स मेथड। मैं आपको क्वेश्चन कराऊंगा और पूरा कॉन्सेप्ट उसके जरिए समझाऊंगा कि ड्यूअल सिंप्लेक्स मेथड क्या है। इससे पहले एलपीपी के मैं सारे आपके टॉपिक्स खत्म करा के आया हूँ। डिस्क्रिप्शन बॉक्स में आपको वो लिंक्स मिल जाएंगे, नहीं तो आप प्लेलिस्ट मैथ्स 4 की उसमें देख सकते हैं। नाउ विदाउट वेस्टिंग एनी मोर टाइम आई एम गोना स्टार्ट विद माय क्वेश्चन। यूज ड्यूअल सिंप्लेक्स मेथड, मैक्सिमाइज मुझे करना है, ये मेरा ऑब्जेक्टिव फंक्शन है, सब्जेक्टेड टू दीज कॉन्स्टेंट्स। अब ये आपको क्वेश्चन कुछ इस तरह हमेशा
Why is it that
Hello everyone, screen. Suppose we are trying to solve this problem. The problem, same at the programming, which is a normal maximization problem. I can start solving this problem using the simple. You see, if I was going to solve the initial problem, I needed to define one artificial variable for the last constraint. Whereas by defining the dual of the initial problem, the need for defining the artificial variables are eliminated. Now to solve the dual of this initial problem, I can set up the simplex table and put all the coefficients inside the table as well
as
the right hand side and the coefficient of objective function and start solving it.
So
As you
she takes her
see, the
max.
problem has been simplified. Instead of defining artificial variables for the initial problem, we eliminated that need, and we're just solving this problem with only slack variables. And we don't need to add those artificial variables and those big M in the objective function. Problem's condition is it is important to eliminate these steps and find a solution to the problem by setting up a simplex table for the initial problem. Let's see how we can do problems. Our problem must live in the row of z, so equals and go to the right hand side. This negative value in the right hand side of the problem, which in this case is negative 150.
So
This way we can define the by negative condition, the set to continuous condition. So we are at the final table of the simplex.
So that's her how she did it that way, but like
Without normalizing a problem, without writing the dual of this problem, and without standardizing it. So what we are trying to do is to eliminate these steps and find a solution to the problem by setting up a simplex table for the initial problem. Let's see how we can do this. But before we start solving this primal problem using the dual simplex method, it is important to know that we cannot use the dual simplex method for all linear programming problems. Our problem have to meet two conditions to be able to be solved with dual simplex method.
okay, we
The
should
first
listen to that.
condition is the objective function must satisfy the optimality condition. It means that if it's a minimization problem, all its coefficient must be positive, and if it's a maximization problem, all its coefficients must be negative. Because if you standardize this objective function and setup must be positive, and if it's a maximization problem, all its coefficients must be negative. Optimality condition. It means that if it's a minimization problem, all its coefficient must be positive, and if it's a maximization problem, all its coefficients must be negative. Because if you standardize this objective function and set up the table of simplex for the row of z for x1 and x2, you get -3 and -4, which are sign of optimality condition. Because for a minimization problem, we stop the simplex problem when we have all the coefficients negative in the row of z, and for maximization we stop when all the coefficients are positive in the row of z. So if the coefficient of objective function are all positive for minimization, or the coefficient of objective function are all negative for maximization, it means that we have optimality condition for the objective function. The second condition is we have to have at least one constraint with greater than or equal sign. So these are the two important criteria.
Okay, so I have both those things for this one. So we can actually do the dual simplex method. So essentially all is that we just have to change it and then solve this, right? Okay, so this is literally plug and play. So we go 12y1 plus 22. Oh. Add. Is this slack or surplus? Add surplus. Oh, wait. This is slack. Okay, so we're gonna add slack variables. So we're gonna give it S and T. We're just gonna make this 4y1 plus 2y2 plus 5y3 plus s 9 4. We're gonna go plus 4y2 plus 2y plus t, and then there's our slack, and then we're going to do our dual simplex method, which is going to be, this is equal to what, w. We just bring everything to the other side, so what we get is, what am I doing? We're going to go y1 y2 y3 st. I should make that a little neater. T, and then W. Okay. What we got is 9, 3. Is this 0 for now? Yep. 1 second.
Of an initial problem without actually
Oh. Okay, well, they do. Okay. So what we have is negative 12, 22, negative 34, 0, 0. What we have here is 4, 2, 5, 1, 0, 1, 4, 2, 0, 1. And then we take the most negative, which is this, and then it's this column here, and then we divide by the number. So 9 over 5 is probably bigger than 2 over 3. Let's see. 9 over 5, 1.8, 2 over 3. Or 3 over 2, sorry. 1.5. This one is our pivot column. Okay. So we're going to take row 2 and times it by 1/2. So I'm going to give myself extra room. Okay. 3 over 2. We go 4, 2, 5, 1, 0, 0. 1/2, 2, 1, 0, 1/2, 0. And this is negative 22, nope, negative 12, 22, negative 34, 0, 0, 1, 0. Okay. So if this is our pivot, we got PP. This will be Y3 right now. Okay. And then we want to get rid of the top and the bottom. So to get rid of the top, we multiply this by -5 and add up. So first off, okay. Okay. We're going to keep this first one.
and dual simplex method has concluded. Please refer to your Blackboard for your assignments. Which is x2 in this feasible problem in an optimality condition can be solved using the dual simplex method. Now, if I had a maximization problem, the optimality condition is to have all the coefficient positive in the row of z, but we are looking at a minimization in this. We have all the negative value, which means it's the positive our problem by setting up a simplex table for the initial problem, and find a solution to the problem by setting up a simplex table for the initial problem. Let's see how we problem and without. Now we can introduce the concept of dual simplex method. In dual simplex, we're trying to solve the dual of an initial problem without actually going through these steps here, without normalizing a problem, without writing the dual of this problem, and without standardizing it. So what we are trying to do is to eliminate these steps and find a solution to the problem by setting up a simplex table for the initial problem. Let's see how we can do this. But before I start solving this problem using the dual simplex method, It is important to know
So
that we
this
cannot
all
use the
feels
dual
right.
simplex method for all linear programming problems. Our problem have to meet two conditions. The object function stop the simplex than or equal met this condition, we can easily standardize this problem by adding just slack variable, because according to the definition, you see that all the coefficients in the row of z are negative, which means for a minimization problem of the pivot row, the coefficients of the pivot column must be of the third row in the pivot column to 0. We need to implement this multiplied by the fourth row in the new table, the dual simplex method by finding the most negative value here. But as you see, there is no negative value in this right hand side, and also the optimality condition here exists. So we are at a feasible solution, and we also meet the optimality condition. So we are at the final table of the simplex. If I had negative values in the right hand side, I had to continue selecting the most negative value and implementing the minimum test and continue the table. But here, since all the values are positive, we have reached the optimality condition and z star is 300. So as you see, from optimality condition with infeasible solution, we got to the point that we have both feasible and optimal condition. So we are at the final table of the simplex. With this, our lesson in dual simplex method has concluded. This is the new second row that I get. The elementary row operation to change the first element of the pivot column to 0 is -1 multiplied by the fourth row in the new table plus the first row in the old table, which if I implement, this is the new row that I get. Again, as you see here, every time we multiply the pivot row by something and then add it with the row that we want to see the change in it. The elementary row operation for changing the row of z is -2 multiplied by the pivot row in the old table plus the row of z in the previous table, which if I implement this step, this is the new row that I get. Now we have to continue the dual simplex method by finding the most negative value here. But as you see, there is no negative value in this right hand side, and also the optimality condition here exists. So we are at a feasible solution, and we also meet the optimality condition. So we are at the final table of the simplex. If I had negative values in the right hand side, I had to continue selecting the most negative value and implementing the minimum test and continue the table. But here, since all the values are positive, we have reached the optimality less than or equal condition. Table of the simplex, you see that all the coefficients in the row of z are negative, which means for a minimization problem, we are in the optimality condition. But in the right hand side of this problem, you have a value that is negative, so the problem is infeasible. That's the initial requirement for starting a problem using the dual simplex method. So you have to start from a table that is optimal, and your right hand side at least have one negative value, which means it's infeasible. So infeasible problem in an optimality condition can be solved using the dual simplex method. Now, if I had a maximization problem, the optimality condition is to have all the coefficient positive in the row of z, but we are looking at a minimization in this example. Now, the way that the dual simplex method works is this time we have to look for the most negative value in the right hand side of the problem, which in this case is -150. This way we can define the pivot row. After defining the pivot row, we have to implement the minimum test, but this time the minimum test is implemented by dividing the non-zero value of the row of z by the negative value of the pivot row. So non-zero value of the row of z are -3 and -4. For the implementation of the minimum test, we divide the non-zero value of the row of z by the negative value of the pivot row, -1 and -2. And we do not consider the signs when we do the minimum test. So you do this test without considering.
Okay, so you do the test without signs, but I mean, like, even still, like, let's do Shaun of the Dead. Okay, so for this one, okay, we have our primal problem. What we're gonna do is the dual simplex methods, which I just learned. Okay, so this one. Ooh. So it's a minimize. So what we want is
the negative signs that we see here. If I implement the minimum test, you'll
so I want these. If I want a minimum,
see that the first three constraints of this problem can be easily standardized by adding slack variables, because all the constraints are in form of less than or equal, and by adding slack variables we can standardize this problem. However, for the last constraint, we first multiply it by a -1 to change the sign of the constraint to less than or equal. And then when we have this condition, we can easily standardize this problem by adding just a slack variable, because according to the definition and the concept of slack variables that we introduced earlier, we can add one decision variable to the left-hand side of this problem to make it equal to the right-hand side. So the problem is standardized, and we can store the dual simplex method. So if I say
okay, so for this we'd have to add surplus variables, but it's minimize. We're gonna change this so that we can have less than or equal to. So what we're gonna get is -4x1, -x2. We're gonna add a slack variable 1, 12. And then we'll get -4x2. And we're gonna add a second slack variable, less than or equal to 22. And then we'll have 5x plus 2x2 plus s3 less than or equal to 34. Okay. Okay, that's a standardizing it. Yeah, whatever she said. Didn't quite understand it. Gonna try it anyways. Yeah. Anyways, so now that we've done that, what we have to do is we have to create our table. So now we have our table of this. Okay, so I'm gonna try and make it neat like she did. Yeah, S1, S2, and S3. That's cool. I'm gonna try to organize it like she did. She did a really good job. Okay, so we go like this.
Can you hear it? Yeah, ready? Yeah.
We go bigger. Okay. She had 4, but she had also 4 constraints. We do not have 4 constraints. Okay. This is our right hand side. Okay. We got S1, S2, S3, and Z.
Revolution with a solution. We're gonna take it to the overload. Rebel radical retribution. We're here to get what we are owed.
Okay.
I think my head is gonna
Okay.
I think my head is gonna explode, yeah. I think my brain is gonna
I'm actually gonna listen to some. No, I'm not. Okay. So now we're gonna take this. We're gonna go 4x. -1, 0, 0, right hand side 12, -12, -22, 34. Okay. 4, 0, 1, 0, 5, 2, 0, 0, 1. And then it's -9, -3, 0, 0, 0. Okay. Now, what we're doing is this is a maximize and this is a minimize. So this is good. This is optimal. So this is optimal right now. Okay, but we want for maximum we want these to all be positive. So what we're gonna do is we're gonna take the most negative of them. Okay, so the most negative is this one, and then what we're gonna do is divide by these things to find the lowest number. So we're gonna say 9 divided by 2, which is 4.5, and 3 divided by 4, 7.5. These are our pivot points. Okay. Okay.
Set up the initial table of the simplex. You see that all the coefficients in the row of have for the slack variable for the pivot row of the previous table. It doesn't matter what pivot row we are using in the old table.
Okay. So how should I do this? S1, S2, S2, because it's a cool way to do this.
Or new table at least take this row by value test. So you do see that it must be changed to 1 in the next table, and all the other coefficients of the pivot column must be changed to 0. Okay, so the first thing in the next table is to replace S4 by X2, the decision variable related to the pivot column will seats instead of the S4 slack variable for the fourth constraint, and the elementary row operation for changing the pivot value to 1 is dividing the fourth row by -2, which if I implement this step, this is the new pivot row that I get. For changing the element of the third row in the pivot column to 0, we need to define an elementary row operation. What I did, I used the old pivot row to define this elementary row operation. I'm multiplying this row by 2 and then adding it with this row. I could have alternatively used the pivot row in the new table and multiply this row by -.
Okay. So what we're gonna do is we got to get rid of, so this is our S3, so for this row, oh no, S2, so we gotta our pivot point was here, so we divide by -4, so S2, S3, so we get is negative, oh no, 1/2, 1, 0, 1, 4, negative 22 divided by 4. I don't think that ends up with anything. Nope. 11 over 2. Okay. And that is going to be row 2 times -1 over 4. I should say -1 over 4 times row 2. Okay. Then we want to, let's do the next top row. Ooh, okay. Let's go up. If I want to get rid of 1, I just row 1 plus row 2. So this will be 0. This will say 1. This will say -1 over 4. Okay, that's correct. Yep. And then 1, 0. Now a half plus -4. So that's -8 over 2. -7 over 2. And then 11 over 2 plus 24 over 2 24 minus 11. Over 2. 13 over 2. Negative. Okay. Okay, and then we want to get rid of this 2 right here. So if I want to get rid of this 2, I'm going to take this 1 right here and multiply it by negative 2. So we're going to go negative 2 times 0, 2 plus 0, 3. Negative 0. Okay, so this is negative 2. So negative 2 here is going to be negative 1 plus 5, 4. It's going to be 0. Negative 1, 4 times negative 2 is 1/2. And then this is going to stay 1. And then negative 22 over 2. Is that right? Negative 22 over 2. Negative 11 plus 34. Minus 11, 23. And then we gotta do it with the bottom row. So to get rid of this negative 3, we multiply by 3, so that's going to be 3. So 3r2 plus r4. Okay. And then, so 3/2 plus 9, negative 18, wait, 3/2, right? Yeah, 3/2, so that'd be 15 over 2, negative 15 over 2, 0, this will be negative 3/4, and then negative 33 over 2, negative 33 over 2, that's here is negative 33 over 2. Okay, now, we have an issue, we don't have this to be both negative, and we don't have this to be both positive. So
4 and added with the third, the pivot, the new plus the first row. See the change. This is the new row that I get. Now we have to continue the dual simplex method by finding the most negative value here. But as you see, there is no negative value in this right hand side, and also the optimality condition here exists. So we are at a feasible solution, and we also meet the optimality condition. So we are at the final table of the simplex. If I had negative values in the right hand side, I had to continue selecting the most negative value and implementing the minimum test and continue the table. But here, since all the values are positive, we have reached the optimality condition and z star is 300. So as you see, from optimality condition with infeasible solution, we got to the point that we have both feasible and optimal conditions.
Okay,
so we are at the final table of the simplex.
Here.
With this, our lesson in dual simplex method has concluded. Please refer to your Blackboard for your assignments.
Okay. So now we do this again, and this time we're replacing.
Okay, in this video, I'm going to use the
Okay, so this is what? S1? Being replaced by S1? Okay. X2. So, first of all, this is going to become, we're multiplying it by negative 4. So negative 4, 0, negative 4, negative 2, 3 times negative 4, but it's actually times negative 2, which is 26. 0. Okay, now, so this would be times row 1 times negative 4. Okay, x2, we want to get rid of that negative 1/4, right? Below us. That's what we're going to get. So 1 plus this. So that's what I want to do, is this plus this, okay? And I want to get rid of this negative 1/4, so I multiply this by 1/4. That's it. Plus 1/4. So 1/4 R1 plus R2. It's going to be 0. 1/4, that's going to be -1. So we want, and then 14 over 1/4 plus 1/2. So 14 over 1/4, no, is going to be 7/2, 8/2, 4. Oh, that worked out nicely. Okay. 26 is over 4. 26, does that divide by 4? It does not. So 16, 13/2, 13/2 plus 11/2 is 24/2, which is going to be